Yes, are we waiting or we should proceed? Hello, please, are we waiting or we should proceed? Oh, please, can you hear me? Hello.
Yes, Doc.
So are we waiting or should proceed?
I think we should proceed. They will join us later.
Okay. So let's start. Okay, so we are considering a minute. Physical chemistry 1. I mean 2. So it means that we've done the 1 and then we are looking at the 2. Is that correct?
Yes, Doc.
Okay. So it's just the other part of the physical chemistry. There, it's not much related, but then just an extension of physical chemistry. It's also not all aspect of physical chemistry because we've left some parts out which belongs to the physical chemistry, but then on the lower level, like in level 200, it's quite difficult to take in those. So we take that out of the physical chemistry. What I mean is that in the physical chemistry 1, we considered some introduction aspect to thermochemistry, then chemical kinetics, then electrochemistry. And then we're going to advance in other aspect of physical chemistry, like chemical equilibrium, acid and bases, and then solubility. But then there's also the other aspects like quantum mechanics, which is under physical chemistry, of course, thermodynamics, which we considered just introduction as a thermochemistry. So we can't deal with all the full aspect of the physical chemistry, but just a few parts. So today we are just looking at the physical chemistry 2, and that covers only 3 main aspects, just as the physical chemistry 1. So at the end of the course, we'll just be looking at or be dealing with chemical equilibrium. We want to understand what goes on in a chemical reaction. We'll also deal with acids and bases. Then we'll deal with solubility, which will cover just some properties of their solubility, especially the solubility product. So that's what we want to really look at. So what we're going to do is that I'll take them one by one and then deal with that. So we want to look at just this chemical equilibrium. Later, we'll look at the acid and bases. Then the last part will be the solubility. So we want to look at that chemical equilibrium. Well, in that chemical equilibrium, I'll also kind of split it more. So we'll look at this, what is this chemical equilibrium at all? Well, we can build it up from chemical reactions to where we establish equilibrium in the chemical reactions. We'll look at that. We'll look at some types of this equilibrium that we can obtain. Then we'll do some few calculations there, where we'll look at the equilibrium constants for in terms of concentration, and then of course in terms of pressure as part of the factors. So we'll look at some factors that affect equilibrium, which temperature and pressure is part. Then we'll look at the relationship between that product and then the two products in terms of pressure and concentration. And we'll try to see if we can, when we have equilibrium, a reaction, whether to be able to predict how the reaction is going to go, whether it's going to move to the forward or it's going to move to the backward. That's where quotient comes in. So by calculation, we can calculate and then predict if I'm having a chemical reaction going on, which one will be more favored because it's equilibrium. It can move, it can be for favoring the product, it can favor the reactant. So which one will be more favored when I'm dealing with that reaction? So once I'm talking of predicting where the change will be happening or which part will be more favored, then we'll consider the principle. This one we are not just predict doing any calculation, but just we are just using this principle to predict. And the principle is just what we call the Le Chatelier principle. And um, just a little background before we hit that. That is what happens when you are in a classroom and you want to beat students or people in the classroom. Now you raise the cane, then that people hold the cane. Now what it means is that if care is not taken, there's going to be a reverse of reaction. So he has been receiving lot of stress, beating, beating, beating. Now that student is fed up. So he gets the cane and sometimes throw the cane away somewhere. Okay, so that's a principle we want to see if we can apply it. And then we'll do some few calculations to this chemical equilibrium, and then we'll just move to a different topic. So that's what we want to do now. Now let's look at this chemical equilibrium. So I think I've stated what we're going to be trying to do. At the end, we'll do some calculations and look at what those calculation means. We'll try to demonstrate one or two examples there and try to also look at the Le Chatelier principle to predict whatever change will be happening. Please, I don't know if you can hear me. If you are not hearing me, quickly draw my attention. I don't want what happened
Can
yesterday.
I hear you?
Okay,
Yes, Doc.
because yesterday I spoke almost 30 minutes and then I realized that I'm off track. Okay, so that is what we want to be looking at in this particular course. So I hope this one wouldn't be a problem at all. So again, if of course it's physical chemistry, so it involves one or two calculations there. So your calculator should be closer so that when we hit the ground, at least you also do something. Well, let's start then. So we are looking at chemical equilibrium. So where is this coming from? Basically, we'll try to say that we are going to be looking at where the origin of chemical equilibrium is starting from. And so just as the name will be, chemical and then equilibrium. Now, when equilibrium is established, meaning that both sides are at peace. So if you have a balance and then you weigh 10 grams and then hang 10 grams, they should all be at equilibrium, meaning they should all be on the same level, the same size. That's what equilibrium basically means. And we are looking at it in terms of chemical reactions. Now, for every chemical reactions, what do we know? We build a concept by, I mean, there's an introduction of chemistry. And we will say that if you want to really define what chemistry is basically we're trying to study matter. And what is this matter? Okay, well, chemically want to study this matter, but matter basically is also anything that should have a name, number one. It should be able to have weight or mass, and at least it should have a space which is occupying, that is volume. And so a ghost is matter, true of us.
True.
Okay, so which space is it occupying? Uh,
It is occupying an empty space.
So an empty space is a space. So it's just
Yes,
like
Doc.
you saying that, okay, so oxygen, does oxygen exist? You say yes. Where is the oxygen? Which
Yes,
space is oxygen occupying? Well, oxygen also occupy a space. If you want to know physically how oxygen is going to occupy a space, then you need to get more of this oxygen, billions of this oxygen. So if you want to know the space that a ghost is going to be occupying, then catch more ghosts. You see a lot of them. Then you just add that. But we are trying to study that. Now, once it has a name, we can study it. And so when you are trying to study it, I always want to tell this story where this studying of matter we want to go down. So we'll go down and then we'll see that okay, it's just some soft particles that really comes together to form what we call atoms. And these soft particles are these electron, protons, and then the neutron. Now, these atoms, of course, still we don't see it, so will come together to form these elements, the same type of atoms. So we say that atoms are, elements are atoms of the same kind. So they form these elements. And so now we can see these elements and we begin naming them. So we give these elements names. And of course, once we can see them means that we can weigh them. So we have the atomic masses for these elements. And so they will get to have a particular volume which they're going to be occupying. Now, these elements put together will also form what we call compounds, where the compounds can either be on that smaller scale, gas elements. We can have what we call the ionic compound or the molecular compound. Well, the ionic compound can either be just a binary compound that is made up of only two elements, or it can made up of polyatomic elements, different elements coming together to form this compound. So we have the polyatomic say ionic compound or molecular compounds. Now, when these compounds are formed, these compounds can also be combined to form further compounds. Some can even form an advanced compound of just the simple compounds that we have, which we call them the complexes or sometimes clusters. And so, how do we put these compounds together? The process of putting these compounds together is what we are trying. Of course, they are going to be engaging themselves, interacting with themselves, reacting with themselves. So that process is the reaction. And of course, since we are talking of chemicals or compounds, and we say that we call them the chemical reactions. Now, when we put chemical reactions on board, of course, the compounds will also have their name. So compounds we call the individual compounds. We have their formulas which we use to represent them, call them the chemical formulas. When these compounds are put together, they form equations. So we can use equations to also represent a chemical reactions. Now, in that reactions, the compounds that are going to be engaging themselves, reacting with each other, we call them the reactants. That's what we start with. And then whatever we're going to be producing, we call them products. Now, in the equation, when we are trying to write equation, we put the reactant on our left and then the products on our right. Now, we separate the reactant and the product by arrows. Well, these arrows can be in different forms, which communicate differently to us. So when we have a full arrow, then it means that that reaction goes to a completion, meaning the reactant will react to form a complete product, and that product is stable. Then we can have the reversible kind of arrows, a full arrow going forward, another full arrow coming back. That's a reversible reaction. Well, in terms of height, if one is longer than the other, it gives you an idea that, okay, once this arrow is pointing forward, then and it's longer than the one pointing backward, it's not by accident. So when you're writing those arrows, you should know what you are doing because it communicates. So if that forward one is longer than the backward one, it tells us that the forward reaction is much favored than the backward reaction. Then we have what you call the partial reversible reaction. So instead of writing or drawing a full arrow, we draw the arrow leaving one part of that arrowhead. So it becomes half. So we call it partial. So we can have the partial reversible reactions, or even that we also will see how the arrow is going to be like that partial arrow. Some are going to be shorter than the other. So it also tells you which one will be favored. So the point is that we put these arrows there. So the partial arrows there also tells us that either the reactant or the product are equally favored. So the reactant will react to form product. The product again will reverse to form the reactant. So it's just going back and forth, back and forth. You form this within some space of time, you form this, it goes back again, goes back again. In that case, we'll say that it's getting to the point where equilibrium must be established. So a chemical reactions which goes through that kind of changes, then we are saying that we are going to be establishing equilibrium. Well, factors which we try to look at that, if you use physical factors, sometimes in the reaction it will become difficult to observe what is going on. So we have other kind of factors which we use to consider. For example, I will take, say, concentration. And of course, I'll be able to know the concentration which I'm starting with. Now, ordinarily, once I start the reaction, the concentrations of the reactant should be decreasing. Why? Because it is decreasing to form a product. So if you remember the first part, the rate of reaction, you'll see that the rate of reaction tells us that the rate at which the concentration of the reactant is decreasing to be equal to the rate at which the product is going to be forming. Is that the same concentration? We are not creating, we are not losing. So that is what is going on. So I can use concentration to know that the reactant is decreasing, and then the product concentration, which was at the point nothing was forming, so we say the zero concentration now increasing. It will get to the point where the concentration of the reactant is not going to be decreasing again, and then the product concentration is also not going to be increasing again. At that point, we will say that equilibrium is established. Please, are you following my story?
Yes, Doc.
Okay. So we will see that some reactions does not go to completion. It's not every reaction that goes to completion. I think this is a little bit matured class, so I wouldn't use that my example which I use for my these children who have been coming to university, young girls who come to the university, and then they'll come and say that they are preparing palm nut soup. So they'll put their tomatoes, they'll put their fish, and then they'll prepare their palm nut soup. They'll put the palm nut soup there, and maybe they keep it in the fridge. The following day, they will see some separation happening there. The water separating themselves from the and the peanut and then the tomatoes group. This is purely reversible. It's going back. Okay, so whatever they said there, that reaction was not complete. It didn't form any complete reaction. It was separated. So it's going back to the starting material. So that's where we are saying equilibrium is going to be established. What do we observe during equilibrium? Number one, we'll see that at equilibrium, the rate of the forward reaction it will be the same as the rate of the backward reaction. So at least I'm taking it from the chemical kinetic point of view, which I know you are aware of. So, and I'm sure you remember this rate of reaction. Okay, you remember that?
Yes, Doc.
Okay, so we try to move on then. Yes, that's one point. Now, what we should sorry, I repeated that. I'll delete one. So that's one point. Now, at equilibrium two, you're going to see that the concentration of the reactant is going to be constant. It's not going to be changing, as the concentration of the product is also not going to be changing. It will just be constant throughout. So when you are measuring, you just be checking the concentration changes, and then at the point you see that for some time.
Hello, colleagues. Good evening. Please, going on or doctor has not come yet because I've just joined. I'm not getting any.
Doctor is
Hello?
saying, but it seems he has gone off.
Oh,
Hello?
okay. Okay.
Is this a chemistry online, chemistry major?
Yes, please.
Oh,
Yes,
then
please.
okay. Thank you.
I think we should alert him that he has gone off. Oh.
Yes, so we have to alert him.
Okay, he's back.
We need to prompt him that he went off.
Hello, can you hear me now?
Yes, please.
Okay, so I think I've not gone far. I was still on this slide.
Yes, Doc.
Please, is that correct?
Yes, sir. The rate of forward reaction.
Yeah, so at equilibrium, the rate of the forward reaction is also is the same as the rate. So the rate at which the concentration is going to decrease with time is also the same as the rate at which the product is going to be increasing with respect to time. That's what I mean by the forward reaction will be the same as the reverse reaction. Another thing that we should also note is that when equilibrium is established in any chemical reaction, what we'll see is that the concentration of the reactant is not changing; it becomes constant, as compared to the concentration of the product, which is also not changing. It's just the same thing. And what I mean is that it's not like the concentration of the reactants are fully used. So it has formed product. That is why it is not changing. But then the concentration of the reactant is the same as the concentration of the product. It's constant. Please, you get it.
Yes, please.
So for example, I'm starting a reaction and I'm using, say, 6 mole per dm cube. Then 6 mole per dm cube is going to be decreasing at a point, say, at 2 mole per dm cube, it is not decreasing again. Now I go to check the concentration of the product, and that's the concentration of the product is 4 moles per dm cube. Well, that is not equilibrium being established. It means that the concentration of that is fully used. But what I want to say is that, well, equilibrium will be established when, like, out of the 6, 3 moles is being used and 3 moles of the product is being formed. Then at the time, the 3 moles of the reactant is not changing, and then the 3 moles of the product is also not changing. They are the same. So equilibrium is established. Is that okay?
Yes,
Well,
sir.
if you consider equilibrium in terms of the Gibbs free energy, which is related to the entropy and the enthalpy, we'll say that when equilibrium is established, when a reaction is complete, well, it's going for a completion, there'll be the disorderliness there. But when equilibrium is established, the Gibbs energy, it's zero. There's no kind of disorder because, as I mentioned, the concentrations are just the same. And of course, there's nothing going on. It remains the same. So there's no disorderliness as in the forward or the backward reaction. Nothing is changing. It's just the same thing. So it remains at that kind of zero position. So that is what happens during equilibrium. So if you want to know or understand what actually is going on during equilibrium reaction, then that is what we can just observe from that. At least 3 things, 4 things that we can observe in equilibrium. Come again. Are you asking a question? So I can't hear your question. Oh.
It's not a question.
Okay. So then let's go on. Well, let's look at equilibrium in general, the totality of what equilibrium is all about. Well, if we talk of equilibrium, we can just group it into 3 types of equilibrium. General equilibrium, not just a chemical equilibrium. Okay, so we can talk of the so-called the thermal equilibrium, meaning heat kind of change. Now, I think if you also recall when dealing with this thermochemistry, for example, okay, we're going to see how do we then measure the temperature of a body so that we can now say that the body or the person's or the patient temperature is say 37 degrees Celsius. But basically, if we can get to that mark, what it means is that the temperature, I mean the thermometer and then the body which we are measuring, the patient's body is at equilibrium. That is why we could then conclude and say that otherwise it will be rising till the thermometer and that body becomes equilibrium. They'll be in the same equilibrium so that we can record the temperature of that person. So the mercury becomes equilibrium with whatever going on. So that's so there's no temperature changes in that system. We call that the thermal equilibrium. Well, we can have the static or what we call the mechanical equilibrium. That has to do with motions when there's something going on. I mean, mechanical, there's something going on, whether a change in speed and those stuff. But once equilibrium is established, then it means that there's no kind of changes. The speed is there, the same speed which is still going. Then we'll look at the chemical equilibrium, which is our focus. We'll look at this in a reaction. So whatever changes that is happening in a reaction, what is actually going on in that chemical equilibrium. Well, when we take the chemical equilibrium, we can say that we'll look at it in terms of physical processes, things that we can see, or the chemical processes. Well, in the physical processes, we're going to see that some of them we can observe when equilibrium is being achieved. But then in a chemical equilibrium, we'll not see whatever is going on. Now, for example, you have a cup of water. Then you put in a salt, maybe 1 teaspoon of salt. When you put in that 1 teaspoon of salt, the salt disappears. Then you put in another 1 teaspoon, it disappears. You put in another 1 teaspoon, now the salt is not disappearing again. What do you think is happening? Can somebody help us?
Solution has become saturated.
So in that case, you see, we'll say that that's actually what you are seeing, and you are calling that, you are saying that it has been saturated. It's actually a formation of your salt. The salt actually has dissolved. The sodium chloride has dissolved. Now, what you are seeing in that your water is new formation of a new salt. So a chemical equilibrium is actually a dynamic kind of equilibrium. It's kind of changes. So because you are not seeing what is happening, the first one, it was just a straight completion. It went to completion. The second one was when the salt was accumulating and going to be fighting back. So first, because the water was plenty, you just vanish there. Now you are putting more salt. So they are also gathering to come against the water. And so chemical equilibrium will say that it's quite dynamic. It's going to be changing. Although we don't see it physically, it's going to be changing in that kind of form. But if you want to really take this part as in the chemical equilibrium in terms of the physical processes or the physical equilibrium and then the chemical process, then we'll try to say that we'll look at it, for example, a liquid and a solid, just as I gave that example. Okay, in a liquid and a solid situation, equilibrium can be established. And of course, gas and solid and whatever. So in all the physical things that you are kind of experiencing, seeing, you can actually see that and then you can observe that. Let me give you, say, an example of this solid liquid equilibrium. So for example, there is this melting of a crystalline solid. Well, the conditions are just at a particular temperature, and then the pressure is also going to be constant, where the temperature which we are just measuring or looking at it is just the temperature where the solid is just going to. So let's take ice for example, ice block. Then we are maintaining the ice block at this freezing point, although we've taken it out, or we can be dealing with a fridge kind of situation and want to observe what is going to be happening. Now, when we put that ice out, and then the ice, of course, once you are not changing the temperature, it's going to be melting based on the temperature which is available. So you get to a point where the liquid, so the ice has melted, but then you still see some ice in the water. And that ice is not going, it will stay for some time. If not for temperature changes, it will still be the same to whatever. So it means that at that point, that solid, that ice is in equilibrium with the liquid which you can find. I hope that is okay. Well, if we look at the, say, the liquid gas kind of equilibrium, we can also look at the evaporation of water in a vessel, which we're just going to see how the gas which we are evaporating now be condensed to say will form. So for example, our LPG, listen, actually, you know that is a gas. And of course, we are, compress the gas for it to now be like a liquid. That's why we call it the liquefied petroleum gas. Of course, when you open it, you see the gas escaping. But then at that point where even when you take your cylinder, you shake it, you see, you feel the liquid in there, whereas it's been shaken. Now, I think they have this transparent one where you can even see the level of the gas in there. So you can shake and it behaves like that's liquid. So means that the gas and that liquid, which you are feeling, is now at equilibrium now. So this is what happens when they become in equilibrium form. So a liquid can be at equilibrium with a gas. For example, the vapor pressure scenario. So vapor, a liquid turn into a gas or whatever. And then a solid can also be in equilibrium with the solid. So in that case, we can say, for example, we can measure the volume of a liquid as a mass. And in that case, say for example, water. Once we know the density, we can say that, okay, if I measure the mass of that water, actually I'm measuring the volume. So there's kind of a similarity here where I'm trying to see how the liquid is going to be at equilibrium with a solid where I can try to measure the mass as well. So basically, physical equilibrium, in fact, in our everyday life, we'll see a lot of this physical equilibrium a lot. We have every day we come into contact with that. I think one aspect which I can say is those times we have this camphor. I don't know if it's no more common again. What is common now is the naphthalene balls. Okay, but then I think those times we're putting them in the clothes. Sometimes they put it in the water to change the taste. I think some came to meet what I'm saying. Either you use the hash of palm nut where you cool your cooler and you or use camphor. But now because
Yes.
camphor is no more, please note that as a chemist, you should know the difference between camphor and naphthalene balls. And some companies deceive the customer by writing naphthalene balls into bracket camphor. Well, if you read their
Doc,
inscription, they will say that there is a caveat
hello.
there. Yes, sir.
Doc, that's what we always tell our learners. So the naphthalene bulb is the same as camphor.
It is not.
Whenever it undergoes sublimation.
It is not. You can, after class, you
Okay.
can check. Naphthalene is a
Okay.
synthetic product, whilst camphor is a natural product. So we
Okay.
extract camphor from a camphor tree. It's extracted from
Okay.
a camphor tree, but that plant is, I mean, it has faded off the ecosystem.
Okay.
It's a camphor tree. Whilst
Okay.
naphthalene will synthesize naphthalene. Naphthalene is basically two benzene rings. So we do the synthesis. We start with benzene, and of course, we know benzene is carcinogenic. So putting two of them makes it even more carcinogenic. So don't go and put naphthalene balls in water to drink. They are going to die in the space of time. Or you put it in your clothes to make your clothes look nice, or in your room. That's why they use it to kill insects. Now, anything that
Okay.
you are using to be killing insects, it is also going to have an adverse effect, only that it is acute. It's not just something which happens, just it takes some time for you to, yeah, that's why it's advised that when you spray your room with mosquito spray, you don't stay inside because you're also going to kill yourself. You wait for ventilation, oxygen to carry some of them to subdue some, and then those that will sleep and then will be burning quells. Indirectly, you are killing yourself. You are packing more monoxide, and of course, you are also inhaling some kind of a propellant which is toxic to your system. So naphthalene can never be the same as camphor. But then what I'm trying to say is that when the camphor sublimes, or I mean the scents and whatever, which we're trying to use, that's the idea. So those companies were just, and of course, the scent of camphor is closer to that of the scent of naphthalene. So the company says that they use that into bracket. So when you buy it, they'll put it into bracket, and then the argument is that they are just telling you that the scent looks like. So they'll tell you to read the terms and condition of their product, which customers don't do. Okay, I mean, there's a lot of deception in the market. I was just reading that, that when somebody drew my attention, it prompted me, and then I quickly went to check. For example, Colgate has written that when you brush your teeth, there is no way that paste should enter into you, should swallow it. Immediately you swallow it, you need to dilute or consult a doctor because it is poison. And then some people will say that when you brush your teeth, don't wash your mouth, keep it in your mouth. You are killing yourself. So I quickly check coagulate terms and condition, and it is written when swallowed, immediately consult your physician. Okay, so they put this caveat there, which kind of deceive customers. When you take them to court, they'll tell you that you didn't read the terms and conditions of their product. So they are exempted from that. So I was just using that as an example that the camphor solid can be at equilibrium with a camphor vapor, or say ammonium chloride, the solid of ammonium chloride can be at equilibrium with the ammonium vapor or the ammonium liquid in that kind of term. So if you are looking at the general kind of features when it comes to physical, equilibrium, then we are looking at it in this way that for every physical equilibrium, there's no way there's going to be an exchange of whatever is involved, the matter which is involved to its surrounding. Once there is any loss, there's no way to be stable, or it will be in equilibrium. So we should note that. Now again, irrespective of how the side will be, whether you are starting with this or you are ending that, the chemical equilibrium is dynamic. Only that sometimes we don't see whatever is going on in that reaction. All that we can now see is a physical that, okay, whatever we started, it looks like the same thing, nothing is changing in that kind of form. And everyday life, we experience a chemical equilibrium or equilibrium every day in our life. So for example, there is on a windy day, you will see that your clothes dries very quickly. Have you observed that?
Yes, Doc.
So what we say is that then there is an equilibrium between the wind, which is a gas, and then the liquid, which is in the clothes. So they tend to be in an equilibrium. So it's just clear, and then say that it will not be as when it dries in the sun, but at least it gets dried up in the normal windy day. Again, we can make some one or two examples from that, like removing carbon dioxide from the bloodstream. Definitely, there should be an equilibrium being established. So carbon dioxide plus water will produce that carbonic acid. And of course, that carbonic acid can also break down in equilibrium to form the bicarbonate and then the acid, which will be in the system as well, so that the carbon dioxide will just also be in the system. So like continuously, we still have this everyday life equilibrium, which we are saying. So again, the common one which I use is the soup that you prepare, especially the peanut soup that you prepare. That it oftentimes happen that if you can't do it well, the following day the separation will happen. A nice separation where you have your water on top of it. So most of the times you go, they'll mix it fast before giving you. Otherwise, when they wait, it's going to separate. Equilibrium will establish where the water will separate itself from the ingredients. And they can't throw the water away and leave only the ingredients. So that is what happens. Now, in equilibrium process, what is going on is that it's purely reversible reaction. So let me explain these two. We have irreversible reaction and then reversible reaction. The reversible reaction are purely those reactions that you have a reactant and then the reactant straightforward will produce a product. There's no way that reaction can be reversed back. You can't get it back. So for example, you have a wood. You burn the wood, it forms charcoal. There's no way you can reverse your charcoal to get your wood again. I mean, it's gone. Like our helicopter crash, it is gone. There's no way we can reverse that reaction if we have power to reverse the reaction to bring the helicopter back so that we can get our statesmen back. It's irreversible reaction. Once it's gone, the forward one-way direction, it is gone. Nothing happens again. But we have the reversible reaction where it goes forward, it can come backward. So we use these partial reactions to represent equilibrium reactions. So this is what happens in reversible reaction. I think I explained earlier. This arrow shows that it is going to a complete, that is irreversible reaction, whilst this tells you it is going to be reversed in a partial way. So in this case, there's no way you are going to be forming any complete product. Unlike if it is a full arrow, meaning the reactant will form a complete product and then a full arrow going back, the product will also break completely to form the reactant. That's a complete reversible reaction. But this is a partial reaction. The product is not actually a complete product, and then the reactant is also not a complete reactant. So they are in that middle where they strike that kind of balance. They are in that equilibrium state. Okay, so this is what happens in a chemical reaction. So we should clear that concept or that mindset where students think that once I have reactant, I should form product. In equilibrium reactions, there is nothing like a complete product. There's nothing like a complete reactant. Please, you get me.
Yes, Doc.
So they are just forming. So the misconception of these chemical equilibrium, which some students fail to clearly understand that there's no characteristics of like complete reaction in that kind of equilibrium system, and it is different from complete reversible reaction. So let's try to change that mindset. So if I write an arrow which is complete, like one top, one down, then this one top, one down, that's complete reversible. It is not the same as chemical equilibrium being established. So note that. Now, in a reversible reaction, what happens is that the reaction can either be a reaction which happens between species. If I say species, the reacting species of the same kind, not like the same type of molecule, but then in terms of phases. And of course, in every reaction, the phase of the reaction is much, much important. And we have like 4 different phases of a chemical reaction. We have liquid phase, we have gas phase, we have solid phase, and then we have aqueous phase. So note that. So the state of that compound must be clear, because when we get to a point, we will note that when it is solid, pure solid, pure liquid, we don't consider them when we are dealing with the equilibrium calculation. And we'll mention something called activity. Okay, so the state of every chemical reaction must be clearly noted. Now, when there's a mixture of phases, like a gas mixing with a liquid or a solid mixing with a liquid or gas, that reaction, we call it a heterogeneous reaction. It has more than one phases. So for example, this sodium oxide reacts with this water to produce sodium hydroxide and oxygen gas. Now, the phases are recorded that the oxygen is a gas. The sodium hydroxide Well, here they write liquid, but ideally it's supposed to be aqueous. That is, it's an aqueous substance. Then the water, of course, water can be liquid, it can be gas, it can be solid, but the common use water is liquid. I mean, we use it as solvent. Then the sodium oxide is solid. And so this is
No,
basically a heterogeneous reaction. Yes. I thought somebody is talking.
oh,
Please, is somebody talking or I should move on?
hello, dog.
Yes.
Hello, dog.
Yes, I can hear
Please,
you. Oh, I can hear you. Please, can you hear me? Can somebody confirm if you can hear me?
We can hear you, Doc.
And so I want to
Dog, we can hear you. The network is
water
not that
and
stable.
aqueous are they similar or there's a difference?
I didn't hear you. If somebody heard what he said, he should communicate to me.
Hello, doc. I said, is there any similarities between water and aqueous? Aqueous.
Well, when we say a substance is aqueous, mean it is soluble in water. The aqueous is coming from aqua, and aqua is water. So a substance which is going to be soluble in water is what we call aqueous solution, or it's dissolving in aqua. Okay, so, and of course, when we say water is aqua, like if you write H2O into brackets AQ, what it means is that you are trying to say that water is also soluble in water. And of course, how do I know that this substance is going to be soluble in water and this substance will not be soluble in water? We use what we call the solubility rules. In precipitation reaction, some elements combine to form a precipitate that's solid. Some elements combine not to form solid when it comes to in contact with water. That's the solubility rules. We have about six summary. We can summarize that rules into 6 forms. So I know that that's how come I could see that this reaction, the sodium hydroxide is aqueous. The rule says that all group 1 metals is soluble in water. All the compounds of group 1 metals are soluble in water, no exception. And this is sodium, which belongs to group 1. So it's going to be aqueous, not liquid. Then it also says that
Okay. Thank you, doc.
nitrates are also, so you can check those solubility rules so you can be able to predict these states so easily. But ideally, when you are writing this, we should, in a chemical equilibrium, we should know the state of these or the phases of these compounds, because they are much important when you want to calculate their constants. Okay, so let's try to move on. So we can also mention that when the phases are the same, then we'll say that we are dealing with homogeneous mixtures or homogeneous reactions. So for example, here hydrogen is gas, iodine is gas. They form hydrogen iodide. That is also a gas. Or we talk of, say, acetic acid being a liquid, then ethanol also liquid. They combine, they produce this ether or the ketone here plus water. They are all in the same phase. The reactants are in the same phase. Then we say that that is homogeneous mixtures. Is that okay? Well, let's try to do, well, what am I saying or what have I said so far? Well, what I've said so far basically is just trying to talk about chemical equilibrium. So I just started by building up what a chemical reaction is, and then to the extent where I establish what a
Okay,
chemical
Doc.
equilibrium is. So chemical equilibrium is basically where the reactants and then the products, the state of the reactant and the product are not changing. There's no further changes, irrespective of how you are changing the time, they will still not change. Now, if a reaction is achieved at a chemical equilibrium, we will say that the rate at which the forward reaction is happening will be the same as the rate at which the reverse reaction is happening. So equilibrium is established, meaning the rate at which the reactant is decreasing its concentration, which it will not change at the point, is that the same as that of the product, also increasing, but it will not change at the point. So the concentrations will be equal, depending on the value of the constant that we're going to be having. So this is what we've tried to, I mean, all this long talk, this is what I've tried to establish. Again, I also mentioned that a chemical equilibrium are dynamic in nature, only that we don't see that, except we extend it to the physical realm or the physical equilibrium. That's where we can see that it's dynamic. But then chemical equilibrium is also dynamic. So I cited the example of the sodium chloride in that water, and by addition, you now see that you are forming back. So it's not like so it's just a sodium chloride plus water giving you a sodium chloride plus water. So the sodium chloride is just going to be breaking down into ions, and these ions can now form back when equilibrium is established, form back, combine again, because they still be in the water. They'll combine again to form the sodium chloride, which you are seeing, and you are saying that a super, say, saturated solution or a super saturated solution has been achieved. My salt is no more dissolving. So we'll say that chemical equilibrium is actually going to be dynamic. Now, for a chemical equilibrium can be achieved between other phases, between solid and liquid, between liquid and gas, or what the three phases we can achieve chemical equilibrium. And what I want to stress here is some misconception when it comes to equilibrium. And I mentioned one, that chemical equilibrium is not the same as complete reversible reaction, where a complete product is formed from a complete reactant. That's one misconception which you have to take, clear your mind from that. So it's not like, so in chemical equilibrium, there's no complete product, there's no complete reactant. Again, in some misconception is that a chemical equilibrium or equilibrium is just a state where the rates of the forward reaction and that of the reverse reactions, the rates are equal. Not that the rate is equal to zero. It's not like there's no changes going on. It's only that at chemical equilibrium, the rate at which the forward reaction is happening is the same as the rate at which the backward reaction is also happening. So it's not like the rate is now equal to zero. Please, do you get the argument?
Doc, please come again.
So I've given you two misconceptions. Which one should I repeat? Okay, I'm stating that.
Equilibrium.
Let me state that again. People think that when we say chemical equilibrium is established, then it means that a complete reaction was happened or had happened, and that complete reaction has now been broken down to form back your reactant. That is not true. So I said that chemical equilibrium is not the same as complete reversible reaction. It's under reversible reaction, but this reversible reaction is a partial reversible reaction. That's why we call it a chemical equilibrium. So when you are writing an equation, don't write complete arrows. Please, do you get me? Let me write let's tell you what I mean by complete arrow. I don't know if you can see my writing. This is a complete arrow. So a chemical equilibrium is not like you write these two arrows and you say that a chemical equilibrium is established. No, this is complete reversible reaction. But a chemical equilibrium is established when a partial reaction is happening, the same length. Do you get me? So what it means is that there's no complete product, there's no complete reactant. It's partial. Unlike unlike this case, there's a complete product, there's a complete reactant. The reactant can form a complete product. The product can also break down to form complete reactant. So that's one misconception I want you to take note of that. Now, another misconception is that just as I'm saying that from here, so where's my cursor? So I said that at chemical equilibrium, the rate of the forward reaction is equal to the rate of the reversible reaction. Fair noted. Is that okay? But let's note that the rate of reaction is not equal to zero, where we say that there's no rate of reaction going on, it is zero. That's a misconception. If we say nothing, if the rate are the same, it doesn't mean that there's no rate going on. There's something going on. That's why we said that chemical equilibrium is dynamic. There's something going on. The fact that you record a change in concentration as against a change in that concentration and they are the same does not mean that the rate of reaction is equal to zero. But then it's happening that the time you are measuring that this one is forming this, at the same time this one is also forming this. The reactant is forming the product at the same time the product is also forming the reactant. So the time you pick the concentration to measure, you will not see anything, but does not mean that the rate is equal to zero. There's going to be changes in the forward reaction and changes in the reverse reaction, only that it is happening at the same time. Will that misconception be cleared?
Yes, please.
Okay, so that is what we should take note of that. So this basically just the introduction of that. Now let's look at the concept into a little bit details as to what is this chemical equilibrium. We want to now understand it and trying to address one or two questions to what actually is this and also put some practice to what this chemical equilibrium is all about. Now, we'll try to see that, okay, we need to address one or two questions here that what happens in chemical equilibrium when the reaction is going on and we say that equilibrium is established, does the reaction always run at its full course so that the reactant are fully used up or not? So basically from the explanations which I just gave, I think you can help me address this question. Number two, does the reaction proceed in the same direction or it cannot, or it can be reversed? Then number three, does or can a reaction reach the point where the reactants are still present, but there does not seem to be any further changes that is taking place in that reaction? Can you help me address these questions? The first one, who will help me? So does a reaction always run in full course so that all the reactants are being used up?
No, doc.
Okay, no, your
I
reason.
think no.
No.
Your reason.
What you just taught us, we can easily deduce that even in chemical equilibrium, when chemical equilibrium is established, there is no complete reaction, or the reactant cannot complete. That's why you give it that too early. It is not complete that the reactant can form the product, so that the vice versa. So if the reactant is forming, so as the product is also forming. So if it happened that way, then I can say that there is no complete reaction. That is what taking what.
So the reactant will still be in the system. I mean,
Yeah.
you can't use it completely.
Yeah.
Okay, thank you. The second one, does a reaction always proceed in the same direction? Or can it be reversed?
It can also be reversed. That's why we have
It
reversible.
can also be reversed. I mean,
Yes.
that's where we are now. So I'm just, this question will now introduce the chemical equilibrium clearly. Now, again, the last one, can a reaction react at a point where the reactant will still be present, but then it does not seem to be there does not seem to be any changes going on?
Yes.
Yes.
Yes,
Okay,
Doc.
so this is where chemical equilibrium then comes in. So we're trying to understand that concept, and this is what chemical equilibrium is all about. Now, look at this image, and then we're going to understand that the image, well, if you look at it, is basically we're having a liquid or a solvent, and that solvent will contain so dinitrogen tetraoxide. In other words, it can be two kind of laughing gas in a tube, which we put in this solvent. Now, what you try to understand is that it's going to be a point where the dinitrogen tetraoxide is going to be converted to nitrogen dioxide. And is it going to be a point where the reaction can be reversed to form back so the dinitrogen tetraoxide is forming nitrogen dioxide? Is it going to be at a point where the nitrogen dioxide will now start beginning to form the dinitrogen tetraoxide? Well, when that begin happening, so we see that in the first scenario, this is the dinitrogen, yes, the dinitrogen tetraoxide in that glass tube with that water there. It's now trying to escape, and when it begins to escape, it begins forming the nitrogen dioxide. Now it will get to a point where all the dinitrogen tetraoxide will be converted to the nitrogen dioxide, but then instead of converting all of them, the nitrogen dioxide is also forming back our dinitrogen tetraoxide. So here we see that the color will be from, say, white, it will be building up to yellow, and then the yellow will be dipping to brown, but that is where the nitrogen dioxide is being formed. But then later we'll realize that this color again is fading back like that, and then it goes back like that. So in that case, we can establish that, well, this is what actually is happening. There's an equilibrium which is being established. So if you really monitor the reaction, you see that the concentration of the dinitrogen tetraoxide was decreasing, whilst that of the concentration of the nitrogen dioxide was increasing. Now, if you look at this graph, you will see that at this point, there's going to be a cross somewhere. Okay, so it will tell you that, well, it means that at a point in time, if we don't really control the reaction, we can be crossing itself, meaning we can be getting the same concentration at a time. Then equilibrium will be established at this point where the concentration or the rate of reaction of the dinitrogen tetraoxide now becomes the same as the rate of reaction for the nitrogen dioxide. So equilibrium is established. Now, if you look at this reaction, This is the forward reaction, and this is the backward reaction. Now, you see that some books will write it this way, but then I've cleared the misconception. So please pardon me, though I've cleared the misconception. I picked it from books, so this is what is there. And so don't go and write the same thing to me that, okay, you said that it is not correct, but you wrote the same thing. So I'm also giving you the same thing. Just as one of my son will always be arguing with me. And that you tell me that this is not good, but you are doing it. So I'm doing it. So that when you stop doing that, then I also stop. So this is not a chemical equilibrium. It's a full reversible reaction. But when it's partial, so again, if you are using the arrows, you use it well. So far established then. So this is the forward reaction, and this is the backward reaction. Now, when we are writing the rate law, if you remember that, now we'll say that R it should be equal to the rate constant times the concentration of the reactants. You remember? You remember?
Yes. I'll just go to the rate constant.
So if you reverse it, then this one now becomes the reactant, which is for the reverse reaction. So the rate of reaction will be equal to the R should be equal to K reverse times the concentration of this. Now, equilibrium will be established when the rate of reactions are the same. So this is what I'm trying to say. So if I pick the forward reaction, this will be the rate of reaction. If I pick the reverse reaction, this is going to be the rate of reaction at equilibrium. At equilibrium. Then the rate, the forward reaction, the rate for the forward reaction will be the same as the rate for the backward reaction. Are we okay?
Yes,
Are we clear?
Yes, Doc.
Okay. Now we'll try to do some the derivation here. Let me write at this point. So basically, if I divide this by KR, okay, if I divide this by KR and divide here by KR, sorry, KR, sorry. Okay, what it means is that this KR will cross this KR. So if I divide this concentration here, so that I'm grouping the K's together, so N2O4, I'm grouping the K's together and then the concentrations also together. So 4. And then I also divide here by N2, N2 O4, the concentrations together. So that I can have the rate constant for the forward reaction divided by the rate constant of the reverse reaction will be equal to the concentration of the product divided by the concentration of the reactants. Do you see that? Please, do you see that?
So Doc, now it is the rate of the forward reaction.
Well, Doc, please. The concentration of the forward reaction.
The forward reaction now, the rate of the forward reaction divided by, so the rate of the forward reaction divided by the rate of that. So that is the rate constant for the forward reaction divided by the rate constant of the reverse reaction is now equal to the concentrations of the product, which is the nitrogen dioxide. So the concentration of the product, okay, divided by the concentration of the reactant. You see that? You see that? But of course, when we're writing the reverse, because there is a 2 here, stoichiometry affected the rate of reaction. So we'll put it there. So it's going to raise the power whatever stoichiometry was there, the stoichiometric coefficient that was there. So this is it. Now, the rate of the forward, and then, I mean, the rate constant is still constant. So we'll put a general K there, or sometimes we write KE, which represents the rate constant, I mean, the equilibrium constant for that reaction. So we are looking at the equilibrium constant. Equilibrium constant is equal to the forward constant divided by the reverse constant, which is basically the same as the concentration of the product divided by the concentration of the reactant. All of them raise the power of a particular order. So here the order was 1, which has to do with the stoichiometry, because here is 1 and here is 2. Please, did you see what I did? Okay. Now I can make it a general
Yes,
form.
Doc.
Okay, so I can. So let me clean this thing here. Erase. Okay, erase sorted. Yeah. So I can rewrite this in this form. That the rate of the forward reaction, which is equal to the rate of the reverse reaction. So that's the rates. I've written them here. And of course, the order here was 1 because it has a stoichiometric 1. That's how we write rate law. So in rate of reaction, we'll say that when the reaction is just a single step, that is, if it is an elementary step, please note again, if it is an elementary step, the order of the reaction is the same as the number of the stoichiometric factor. That is, the mole factor there becomes the order of that reaction. But if it is not an elementary step, then we need to find the order of that reaction. That is where we can use the initial method to find the rates, or can use the graphical mean to find the order of that reaction. It's experimentally determined, except when the reaction is stated that it is an elementary step reaction. That is just a single step reaction. If it is a single step reaction, then the order is the same as the mole fraction there, or the mole factor which is multiplied there. So this is an elementary reaction. So the order will be the same as the stoichiometric coefficient there. So that's how we write that. So we can rewrite this in this form, that the forward reaction, the rate for the forward divided by the rate of the reverse should be equal to the product divided by the reactant to raise the power of their orders. And I'm saying that these are all constants, so we can represent them as constants. And that constant we call equilibrium constant. They did sync well. Okay. Now we can write a general form for this kind of system. So assuming I have a generalized form, a reactant A.
Hello, Doc.
Reactant. Yes, sir. Please let me hear you.
Hello, Doc.
Yes.
Hello, Doc.
I can hear you.
Can't
Just,
we go
go
by
ahead.
saying? Can't we go directly by saying that the constant is by the reverse reaction over forward reaction?
If you say reverse over forward reaction, you are going to change the concentration. And the idea why we are saying forward reaction before reverse reaction is that in every reaction, the forward reaction must happen before the reverse reaction must happen. I hope you agree with me.
Okay.
So that's why we didn't. So that's why we didn't change it in this. If you change it, it means that the concentrations will change. But then the reason why it's forward over reverse is that in every reaction, we hit the forward before we hit the reverse. So a
Hello.
ratio of you seeing the forward as against the reverse should give you your equilibrium constant equation or constant expression. Is that okay?
Yes, Doc.
Okay, so in general terms, we can have a
Hello, Doc.
general. Yes, sir.
Doc, please, the equation given, is it a complete reverse reaction or partial reverse reaction?
Please, I think I sent lawyers who say that I sent a caveat. Or you didn't hear me saying that caveat.
Actually, my network went off.
Okay, so what I said is that this was one example of the misconception I wanted to clear, or I want to clear. Now, this is a complete reversible reaction, and this reaction is not chemical equilibrium. Is that okay? So
Okay.
I want to clear that
Okay.
because some books uses these arrows and then they tend to just leave it like that. But in details, if you want to understand the chemical or the chemistry behind it, I will not take this to be a equilibrium reaction established. This is complete reversible reaction. But then I said that, pardon me, because I also picked them from that some books. So this is what they have written. But again, we are assuming them to be a chemical equilibrium because so we are just ignoring the arrows. We are just pretending that the arrows are just partial arrows. So this is what we should rather be using. Okay, let me
Okay.
see. Sorry.
Because I was a little bit confused.
Okay, so this is how we should rather be writing it. This is a chemical equilibrium reaction.
Rempong, please
Okay,
mute your
so
mic.
this is how we should write it.
Hello,
And I
Doc.
think I cited the example of my
Hello.
son, me telling my son that this is not good, but I'll do the same thing. Then he'll do the same thing, which I said it is not good, and tell me that, but he said it's not good, but you are doing it. So I'm also doing it so that if you stop yours, I'll stop mine. So please just assume that this is just so that we can just move on. Yes, I hear hello there. You can talk.
Hello, Doc. It will be helpful if you could use a board.
Yes,
Hello,
please, let's talk fast, otherwise
Hello, Doc.
I'll be caught in the web. Yes.
I'm saying it would have been of good. It would be helpful if you could use a board.
Doc, my question is, why is it that the this and the moves in front of the this and the concentrations tend to be the this and the power of the concentration?
And I'm saying that in every reaction we have what we call reaction mechanism. It goes through some steps. So you don't just say that I pick a Milo or chocolate and then sugar and then water. Then I mix the sugar and then the chocolate together and I had my tea. So that's a reaction which has happened. That's what you saw. But in actual sense, it is not that straightforward as you saw it. The sugar will have to break down. So it goes through steps. So in every reaction, we have various steps that it goes through before the reaction will be complete. Now, these steps are called the reaction steps. But there are some reactions which are just one step. Once you add A plus B, you get your product. These are what we call the single step or the elementary step. And we have proven by experiment that, of course, the order of every reaction, we have to measure the order by experiment. We don't do calculation to get that. And so by experiment, we have seen that all the reactions that goes through single step, what we call the elementary step, their orders are the same as the stoichiometric factors which we see here. So in every elementary step, the order of the reaction is the same as the factor which that molecule is multiplying with. So it is only for elementary step reactions. For multiple step reactions, we need to find the order. So in that case, the order will not be the same as the 2 here. It can change, and that we should find the rate law. If you remember the 203. So we have to establish the rate law by finding the order, and at a point we even find the rate constant, and we can use the initial method. We can use a graphical method to establish the rate law. But then if it is elementary step reaction, the order is the same as the stoichiometric coefficient. So here, in most of these reactions which we are going to be writing, most of them are just a single step, that's elementary step reactions. So that's why we are taking the order to be the same as the stoichiometric factor. So the rate law here, the concentration of the nitrogen dioxide was raised to the power 2 because it was having a coefficient of 2. Here it is raised to the power 1, which we ignore because it was having a coefficient of 1. Are you okay? Okay, so in general terms, this is how we write the equilibrium constant expression. If we have a coefficient, a stoichiometric coefficient, or a mole ratio here, a mole factor here, which multiplies that reactant, that's the reactant moving to form a product. Our rate constant can be expressed in terms of concentration or in terms of pressure. Well, if it is in terms of pressure, then it means that we are dealing with gases. So we can express it also in terms of pressure, coming from the idea of the ideal gas. So if we can, so the ideal gas basically is, the ideal gas formula is PV. PV is equal to nRT. Is that correct? Okay. And of course, we know that N divided by V is concentration. So if I'm able to express it in concentration, I should be able to also express it in pressure. So pressure will be equal to concentration times the gas constant times the temperature, which we are using that for. But let's note how we can write the equilibrium constant expression using concentration or using pressure. But most of our calculations, we use the concentration. And so to differentiate between the equilibrium constant expression for concentration and that of the pressure, we use K underscore C or K underscore P, C for concentration, P for pressure. Now, K is equal to, so from where we just prove from this formula, K basically is just the product. K is basically equal to the product raised the power, the orders of the product divided by the reactant also raised the power, the order. So it's just basically going to be the concentration of the product, which is D, raised the power, the order, that is the stoichiometric factor, multiplied by the concentration of E, which is also raised the power, the order, which is E, divided by the reactant A, raise the power the order, and B, raise the power the order. I hope we can keep this in mind.
Yes, Doc.
So we can remember this.
Yes.
Okay. Well, if in terms of pressure, later we'll see the relationship between these two. In terms of pressure, we can also say that the pressure of that gas raise the power the order. That is if the product and that of the reactant also raise the power the orders. That is basically also equilibrium expression in terms of concentration and then in terms of the that. So basically, if I want to start and say that, can you write the equilibrium expression? Well, the constant, sometimes we leave it that, but it's equilibrium constant expression for this particular equation. Can we do that?
Yes.
Yes, Doc, you can do
Okay,
it.
so K will be equal to what?
K will be equal to that is in the product. The product, that
Yes,
is
and the product
concentration
is
of
what?
flow. That's the ammonia. That's gas.
Okay.
Ammonia
So ammonia square, right?
by the
Yes, square is
ammonia square
square
Divided by
all over
divided by concentration of
divided by
nitrogen gas.
N
and then multiply by hydrogen also Q. Is that
Yes,
hydrogen
correct?
multiplying by that of the hydrogen
yes,
gas.
Q. Yes,
Okay.
Q.
Okay. So this will be the equilibrium constant expression in terms of concentration, which I think whatever equation you get,
With the
yes. So I mean, I've showed it here. So this is how we write the equilibrium constant expression, which I think I shouldn't waste my time. When you get those equations, you can write them. Three of us.
Yes,
True.
it's true.
True.
that's true though.
I thought I heard false.
True.
Oh no.
Okay. I heard. I think the person was actually talking about this our course. You know, we'll come to Le Chatelain principle where we'll see that at a point the product will be increasing. At a point the reactant will be increasing. So when the teacher was teaching the student, he says that so this point the product will be increasing. This point the product will be decreasing. So there's this student who actually is lost in there. So the teacher also he wrote another equation. So okay, so what will happen to? So he says the product will be increasing. So if it is decreasing, it's correct. If it is increasing, it's also correct. Increasing. So if it is so, we can cite another example so that you try your hands on. Okay, well, that is it. Now, let's look at some conditions when we are writing this equilibrium constant expression. Number one condition is that we don't write equilibrium constant expression which involves solid and pure solid and pure liquids. Again, when we are writing the equilibrium constant expression, we don't include pure solid and pure liquids. Okay, let me give you an example. So I'll write here, say for example, I have HCl. So I have, say, HCl reacting with, say, well, what will be, I want to just, okay, so for examination purposes, let me just put here, so sodium hydroxide, sorry, sodium hydroxide, and of course, you know the product. The product will be what? Sodium chloride, and then water, right? Now,
Yes.
states or the phases of the compound must be clearly stated. And so for hydrochloric acid is going to be aqueous.
And water.
Sodium hydroxide is going to be aqueous. Sodium chloride is going to be aqueous, but the water will be liquid. Okay, oh, my pointer is not moving, but that's that. But so when I'm writing the equilibrium constant expression, I will not include water. I will just write the concentration of the sodium chloride divided by the concentration of the sodium hydroxide times the concentration of the hydrochloric acid. Would that be okay? So the state of the compound must be specified. We don't write equilibrium expression for pure solid and pure liquids. Why? The reason is going to be attributed to what you call activity, or what you call the law of mass action. Okay, the law of mass action basically deals with, we're trying to understand that in every kind of reaction, the mass is going to be proportional to whatever activity is going on in the reaction. Now, for pure solid, pure liquid, there's not much activity going on in that. They are all pure system. So the activity is given, since there's no activity going on, the activity, well, is it this class we mentioned activity and activity coefficient? Was it this class? So if activity is almost like a unit, it means that the concentration, if nothing is going on, the coefficient is almost like a unit. So activity, the concentration is going to be 1. So we give concentration of 1. And so why we are not including the liquid is that it's just going to, the concentration is going to be 1. So for pure liquid, pure solid, because there's not activity going on, the activity, the concentration is given as 1. So even if we write it as part of the rate constant expression, the concentration of the solid and the concentration of the liquid is given 1. So basically 1 times something is off. That's why we don't include that. So in chemistry, the law of mass action is just a kind of a proposition that gives us an idea that the rate of chemical reaction is directly proportional to the products of whatever activity is going on in that product and that reactant. So the rate of reaction is proportional to whatever activity is going on in that reaction, whether for the product or for the reactant. In that case, if there's no activity going on, the concentration is a unit. That is why no activity is going on. And so when we are writing the equilibrium expression, constant expression, we don't give or we don't include, if you include that, the concentration will just be 1. So we don't include pure solid and pure liquids. Is that okay? Now, we should also note some characteristics of these rates, equilibrium constant, which we are just trying to see that expression. Number one thing that we should note is that equilibrium constant that we are going to be finding is actually a ratio of the product divided by the reactant. And that depends on that concentration, the concentrations which we are going to be having. So we write the equilibrium constant expression for gases and aqueous substances, not for liquid, not for gases. We don't include them when we are writing them. Now the concentration influence that equilibrium constant expression. And again, stoichiometry will also influence the constant. So concentration will affect this. If I should put this. So concentration will affect K. The order of that reaction is also going to affect K. Please, do you see that? So that's something that we should take note. Now, the rate, the equilibrium constant is actually dependent on temperature. So what it means is that once the temperature is going to change, the equilibrium constant will also change. Why are we saying that? Well, temperature is related to concentration. Well, if you take it from the gas point of view, ideal gas situation will tell you there's a temperature component there. If you are doing concentration calculation, temperature affects concentration. So once you change the temperature, you are changing the concentration. Once you change the concentration, you are changing the equilibrium constant. I hope that will be clear. Okay. Now at equilibrium, once we have equilibrium being established, we are going to be using the equilibrium concentrations to calculate the equilibrium constant, not the initial concentrations of the reactant and then the product. They are not the same. Unless equilibrium is established, we cannot calculate the equilibrium constant. Is that okay? So when we are calculating these concentrations, going closer down. These concentrations which you are seeing here are equilibrium concentrations. Are you okay? Hey, am I off?
No, please.
No talk.
See the screen. The screen is not
You are
showing.
online.
Okay. So these
You are online by the
concentrations
screen.
here are equilibrium concentration. They are not initial concentration. Like we started initially with these ones, and then we are at a point getting zero for this concentration. Once this, we have initial concentration for the reactant, and this is zero. The whole equilibrium constant is also zero. Do you agree? So we don't deal with the initial concentration. Later we'll see that if we want to deal with the initial concentration, we call it the quotient factor or the quotient expression. Here we'll come to that. So that's a difference. So equilibrium constant expression is for equilibrium concentrations only. Okay. And that's the equilibrium constant is dependent on temperature. It's also dependent on the stoichiometric coefficient of these concentrations that we are having, because the reaction basically is just a stoichiometric. The reaction is just an elementary step reactions. So that is what we can be deriving from that. Is that okay? Okay.
Yes, Doc.
Okay. Hello, please. Is that okay? Well, I don't know if, but I'm online.
Yes, sir.
I'll proceed then. Okay. Now, what is the, so once we are going to be calculating for that, then definitely what it means is that we are going to be getting values for K. So this a concentration. Concentration is a value, and so we should get a value for K. Now, when we get a value for K, what does that mean? So the magnitude of the K gives us an information. What information are we getting? If we calculate, then we'll see that the K is large. That is, it is more than a unit. It's more than one. Then we get an information that the equilibrium will be lying or will be solely dependent on the product, the right reaction. Of course, if you look at for example, if I should take this equation, I calculate and then it is more than one, meaning this concentration is bigger than these concentrations. That is why it is more than one. The fraction is more than one. Do you agree? If these are bigger than this one, then it will be less than one. To be a fraction which is less than one. If the reactant concentrations are bigger than those, if put together are bigger than the products, then it will be less than one. So if it is more than one, what it tells us is that it's much like the reaction will be concentrated or be relying on the products, because that is where that's what is giving the reaction match kind of figure when it comes to equilibrium. So the equilibrium constant value tells us that the equilibrium now will rely or lies or fall on the right side, which is the product, and of course the reaction will mostly favor the product. Now, when the equilibrium constant is below 1, means that the reactants are much more than the product. So then the reaction or the equilibrium lies on the left. Much of the reactant is what is going to be favored. Is that okay? However, if we calculate and then it's almost like 1, meaning the product is the same as the reactant. The concentrations of the product is the same as the reactant. That's why we cross, we get 1. Then what it means is that both, it's a mixture. Both are appreciated. The reactant and then the products are, appreciated. They are both kind of favored. Can go here, can go here. So it stands in the middle. I hope we remember that. Okay. So please keep this in mind. What does the meaning of the equilibrium constant value? What does that mean? Well, if that is understood, then I think it will be okay if we start doing something. Okay. So yeah, I've mentioned this, I've explained this law of mass action, which leads to the activity. And again, if I want to state that, it's just the law of mass action states that for every chemical reaction, the rate of that chemical reaction is proportional to the product of the concentrations of these reactants. In other words, the law tries to explain whatever is going on in that dynamic situation. That's how the dynamic equilibrium can be achieved. It helps us to explain that concept so that we know that there are kind of activities going on in that system. And we know activity is proportional to concentration. So if there is not much activity going on and it's almost a unit, then the concentration is also like a unit. So that is what we try to establish. And again, we said that if we have this general formula, then the equilibrium constant expression will be written as the product divided by the reactant, or raise the power this order of the reactant, both the products and then the reactants. Number 2, when we are writing the equilibrium constant expression, we don't include pure liquids, we don't include pure gas, pure solid, because the activity, there's not much activity going on, so the concentration is 1. So you can write it, but then the concentration is 1, so it will clear it off. So we write the equilibrium constant expression for gases and for aqueous substances. I hope you remember all this. Please approve, then we move on.
Yes, Doc. Well established.
Let's try our hands on these things. So let's try slowly, and then we'll build on that. So now I want to write the equilibrium expression. Then later I give you values to solve that constant. And of course, I will now be playing with that constant expression. So we want to play with this. Try to write this way. Then later we can be playing with this. Either I give you the concentrations for you to find a constant, or I give you the constant for you to find in either concentrations by giving you other concentrations. So let's try just quick one. Just you take one and then you tell me the answer. Just look at it. It's not about I'm working. Just look, let me see the plan fast. So we are given these 3 equations. Let's write the equilibrium constant expression for each. again, have a plan that, or have in mind how we write the law of mass action, how we write the equilibrium constant expression. Yes. The first one, ozone to oxygen. How would it look like?
Ozone to oxygen is going to be oxygen.
So K is equal to what?
K is equal to concentration of O2
Exponent 3 over oxygen exponent 3 all over ozone exponent 2.
Okay. Now the second one.
Then the concentration is equal to.
Please, concentration is not equal to. Is there a constant which is equal to?
Second one will be the
concentration constant is equal to.
Equilibrium constant, not concentration constant. Equilibrium constant in terms of
concentration of.
Then we have equilibrium constant in terms of pressure.
So K equals to.
Okay. So the second one, please check if you're going to be getting something like this. So the first one
is equal to NOCL exponent 2.
Yes, and then the second one is also that. The third one, please check if the third one is going to get something like this. Is that okay?
Multiplied by CL.
Yes.
Okay. Well, maybe I'll give you 1 minute to continue trying and write this as homework and solve them. So this our homework.
Yeah, no, see.
I want the third one for the previous slide, please, if you can.
You mean this one?
Yes.
Okay. So homework, because otherwise you delay me. So try your hands and try to see if you can get to have this one. Well, so write it in terms of concentration. Let's try to write it in terms of both concentration and then pressure. How would it look like? Let's take only this one, just the dinitrogen tetraoxide to the nitrogen dioxide. How would it look like? So KC. So I mean this one. Let's just do this one. This one. Let me underline it. Let's do this one. It's homework, but let's do this one. So the question says we should write it in terms of KC and then in terms of KP, in terms of pressure and in terms of a concentration. How would it look like? Yes. Okay, I think it's almost the same, only that one you use square brackets. So in writing the equilibrium constant expression in terms of concentration, we use square brackets. Then the pressure we use bracket, but then we indicate as P. So if I should indicate, that is what I'm trying to refer to. So it basically will be like the same, only that one we use square brackets and then the other one we use pressure. But then there's raise the power will be the same thing. Is that okay?
Yes,
Okay. So please note that. That's your homework if you want to do that. Okay, let's move on. Now from this, we can have an argument going on. So does it mean that the Kp is the same as the Kc. No, it is not the same. One is in terms of concentration, one is in terms of pressure. And of course, we know the relationship using the ideal gas. Relationship will be P is equal to concentration times gas constant times temperature. So if I want C, it's just going to be pressure divided by RT. So it means that in each case, the RT component must be taken into account. So classically, there can be a quite, well, I'll jump this part. So there can be a relationship between the Kc and then the Kp. But then we'll look at it later. But again, I've already established this thing by saying that when I calculate the K, what's the meaning of it? What it means is that if it is bigger than 1, if it is bigger than 1, it means that there's more product forming. So it favors a product formation. If it is smaller than 1, it means that the reactant is more forming. However, if it is close to 1, it cannot be exactly 1, but if it is close to 1, means that both are favored. So please also note this condition. Okay, so we can be making some deduction from that. When it is small, what happens? When it is big, what happens? Would that be remembered? Okay. Again, also kind of remember this tip which I'm going to give you so that when we hit, you're going to, we have made this deduction when it is bigger, what it means when it is smaller. But remember this, when it is greater than 1, the reaction goes to completion. I mean, this is greater than 1. So I'm quoting this figure. More than 100, some says more than 100, some says more than 1, some says more than 1,000, and those are. The point is that when it is greater than 1, it goes to a completion. When it is less than 1, it is hardly to go at all because the reactant is favored. So if the Kc is lower, I mean 10 to the power minus 5 is lower than 1, the reaction is hardly to go at all because it's favoring the reactant. And again, if you remember, I said that in a chemical equilibrium, there's no complete reactant, there's no complete product. So in this case, if it is the Kc is lower than 1, it means that it's going to be hard for the reaction to proceed to the product. It's favoring the reactant. But then if it is more than 1, it's going to complete, it's going to go to much of the product side so that we'll be getting some scenario like this. So this is what I'm saying. If it is less than 1, it's the reaction will find it difficult to, so hardly to go forward. But then if it is more than 1, of course, it can go for completion. So again, keep this also in mind. We'll be needing it later. Now let's try to see how we can manipulate. Once we know how to write this equilibrium constant expression, let's try to see how we can manipulate it a little. So for example, I have dinitrogen tetraoxide moving to this. The equilibrium constant says that the product divided by the reactant and the product is 2 here, so it's raise the power 2. Is that okay? Okay.
Yes.
Now, what happens if I reverse this equation? I write it such that it's now 2 N2O. I mean, the nitrogen dioxide now moving to the dinitrogen tetraoxide. What will happen to the K? How would we write it? We'll write it like the dinitrogen tetraoxide divided by the nitrogen monoxide. Is that correct? So what inferences can we make from that? Can somebody look at it and tell me?
Doc, please, can you hear me?
Yes, very light, but I'll manage.
Okay, Doc. So that means the second one, the equation becomes an inverse of the first one.
Okay, so what it means is that when we reverse an original equation, the equilibrium constant must be a reverse. That is 1 over the original equilibrium constant. So if this was the original equilibrium constant, when it is reversed to K prime, the equilibrium now becomes 1 over that, a reverse of that. So we reverse that. So when we say reverse, meaning it is just a fraction of the first one, 1 over that figure. So I give you this experimental data to really see if it is true. Let's see if it is true that when I reverse it, it becomes 1 over that figure. Now let's take the first one. So we said that equilibrium constant, we use equilibrium concentration, not initial concentration. I'm sure I remember. So let's put in these values and try to see if we can get the K for that value. So if you take this concentration, I mean, we are just taking maybe this first reaction or the second reaction values, which is changing or whatever. So if you take the first one, the K, which is NO2 squared, the NO2 squared divided by the N2O4. So I hope you can do that and tell me the answer. Please, are you doing that? Hello?
Doc, we are here. We are trying our hands.
Hey, I've paused myself. Please, did you hear what I said?
No, Doc.
Oh, so all this while.
No,
Okay.
please.
So we are trying to establish something that, where's my cursor? When you have the equilibrium constant, we write it this way. Is that correct? Now, when we reverse the equation, we write the equilibrium constant like this. And we are establishing that when I reverse an equation, the equilibrium constant becomes 1 over that initial or the original equation. That is, if we say a reverse equation, then it's just 1 over a fraction of that. And we are trying to establish that whether it is true or it is not true. So I said that let's take this the first part this first equation, experiment 1, and try to establish the equilibrium constant when it was dinitrogen tetraoxide to nitrogen dioxide. And I said that, well, that is already calculated. So if you want to check if it is correct. Then what I want you to do is that when we reverse it now, which is this one, can you calculate the equilibrium constant for us, which is basically like this concentration divided by this concentration square? What is the answer, please? Can you tell me? Well, I don't know if you can hear me. Okay, so maybe I should proceed. Well, if you do the calculation, you're going to see that you're going to get 4.72. Now, if you compare 4.72 to that, what it means is that 1 over 1.12 or 212 is just the same as that. So basically what it means is that if I should reverse the equation, it is just going to be like the same as 1 over the original equation. Is that established? And please note that. So K prime is going to be equal to 1 over K original, which is that. So please note this. Later, we don't need to calculate to be sure, but then we can establish that K prime or the new rate is going to be equal to the 1 over the old equilibrium constant. Is that okay? Please, am I off?
Doctor, okay. Please, you are online. No.
And so yeah. You are okay. Yeah, I just want to be hearing your voice that if it's okay, if I should move on, that kind of stuff. Okay, now with the same data, we can also make another kind of postulate. Now, the other one is that, for example, if I multiply this equation, let's say this equation, if I multiply this equation by a factor, let's say 2, so that this will be 2 moles, this will be 4 moles. What will be the new equilibrium constant? Well, if you do the math here, the old one, so if I should move on, the old one was, I'm taking just experiment 1. So the old one will give me this value. If I multiply by a factor 2, it's going to give me 2 times of this one. So basically what it means is that if I have the original equation and I multiply it by any factor n, the new equilibrium constant will be the old equilibrium constant raised to the power that particular factor which I multiply that equation by that. Are we okay?
Yes, Doc.
So that is number 2. So establish that also. So remember this. That's the new equilibrium when I multiply by a factor. So sometimes we'll just go straight to, you look at the original, look at the new one, then you just quote this value. We don't need to go through by proving that. Now, a third postulate. A third postulate is that when I'm going to be having like different equilibrium constant values, but then I add the equation to get an overall.
Doc, please, can you show me the second postulate, please? I want to snap it.
You want to, so you mean this one?
Yeah, it's not, you can continue. Doc, please continue.
Okay. So the next one which we want to establish is this. Now, if I have two different equations with their own equilibrium constant values. And I sum them to get an overall equation or a net equation. Now the new equilibrium constant will be a multiplication of these two equations. Well, how do I prove that? If I have this equilibrium constant, I mean, if I want to write that, well, then basically I'm just ignoring the value. That equilibrium constant basically is just going to be the product, which is carbon monoxide, concentration of the carbon monoxide raised to the power 2. All right, this touchpad and those things, times the concentration of the oxygen raised to the power 1. Help me complete it. Divided by the concentration of the carbon dioxide raised to the power 2. Okay. Do you agree?
Yes, please.
Yes,
Okay.
sir.
Then the equilibrium constant for this will also be equal to the concentration of hydrogen raised to the power 2, hydrogen gas raised to the power 2. Okay. 2 raised to the power 2 multiplied by oxygen raised to the power 1 divided by, well, the gas, I mean, the water is gas, so we include that, divided by the concentration of water raised to the power 2. Is that okay? So water raised to the power 2. Okay, so that is it. Now, if I add these two equations and I get this net equation, what did I do? So it is carbon dioxide plus oxygen giving me carbon monoxide plus, of course, there's oxygen here, so it's going to, I mean, be more. So carbon monoxide plus the, I mean, these two, they say it forms this water. So if I'm going to be writing it clearly, it means that this will be 2 moles of oxygen here and then 2 moles of hydrogen gas, which combines to form the water. Do you see that? So because all of them are having 2 moles, we can reduce it when we are balancing that to just make it 1 1 1. So when we reduce it, the K factor will change. And when I add it, meaning I'm adding this to this equation to this equation, and of course some will going to cross out. So eventually, it's, if you look at the overall equation for this K3 here, K3 is going to be that of the concentration of water times the concentration of carbon monoxide. Things are, the writing is there bad, but times the concentration of carbon monoxide divided by the concentration of carbon dioxide, and then the how do I call it? Divided by that of the concentration of I mean hydrogen gas. Yes. Now, if you look at it clearly, you could see that this final equation here, if you look at it clearly, this final equation looks like we have reversed this equation. Do you see that? So the final equation tells me that we reverse that equation. So once I reverse it, the new will be 1 over whatever was the original. So K2 is just going to be 1. So I reverse it so that oxygen goes here. And when oxygen goes here, it can now cross. That's why this final, we don't have oxygen here. And now we have this hydrogen coming here and then the water going there. So that's the concept. So what oxygen crosses that. So it's just 1 over, I think, let me take it to a whiteboard if I can open my whiteboard because it's getting messy here. So I mean it, yes, you can see the paint there. So let me copy this so that I deal with that. So clean this thing there. So that, so if I should take my paint, let me increase, oh, where's my cursor? Yes. So I have this CO2. I'll enlarge it. I'm just writing that. And of course, there are all gases, so I just ignore that. Moving to form CO. Moving to form CO. 2 moles, please. 2 moles of CO plus oxygen in this form. So plus oxygen. And the other equation says that 2 moles of water. 2 moles of water is at equilibrium. It's at equilibrium with 2 moles. So normally, as I say it, you should also like be writing it so that this is bad handwriting, so you can get to have the understanding clear. So 2 moles of hydrogen gas plus 1 mole of oxygen. So, okay, so plus 1 mole of oxygen. And we want to achieve a net equation. We want to achieve a net equation. Let me underline that. So the net equation which we want to achieve is that we want to get to have carbon. Okay, let me put it down here, but I'll clean it. Carbon dioxide plus hydrogen gas moving to form carbon monoxide. Pardon me, carbon monoxide and then water plus water. Okay, so this is what we want to achieve. Now let me make it by a bit plus water. Aye. Oh shit, sorry. Plus water. Okay, so let me make it big. I don't know if you can see my whiteboard. So I'll clean this one. Okay, so please just pardon me. Let me just do this. But so if you'll be writing it also, you write yours as I say it, you can write it and then, okay. Now, if I want to achieve this, what it means is that this equation, this equation must be maintained. The equation 1 must be maintained, and then equation 2 must be reversed.
Hello, Doc.
Yes, sir.
Per the equation 1, the first is two moles of carbon
yes,
monoxide.
So 2 moles. Oh, so sorry, I've cleaned. So 2 moles of carbon dioxide to 2 moles of carbon monoxide and 1 mole of oxygen. Then the second equation, 2 moles of water to 2 moles of hydrogen gas plus oxygen gas.
Yes,
Is that okay?
Yes.
Then we have a K that will be where's
Hello, Doc.
Yes, sir.
Doc, please, I want a little explanation about how you got this in the carbon dioxide and then this in the hydrogen gas at the left side.
You mean the overall equation?
Yes, the overall. Yes.
That's what we are trying to get. So this is the overall reaction. Where is it? What happened? Please, a minute. My listen is not really. Wow. It's okay. It changes color to white. Yes, this is the reaction which we are dealing with. And so it's left for us to see how these two equations can be combined to form this equation. So this is what I want us to look at. So from that overall reaction, what it means is that this equation was reversed. So if it was reversed, meaning that now it's going to be 2 moles of hydrogen gas, 2 moles of hydrogen gas plus 1 mole of oxygen, okay, to produce 2 moles. Sorry, I think to produce 2 moles of water. Where's my cursor? Yes, to produce 2 moles of water. So when we reverse it, this is what happens. Okay, so this is the equation 2, and then we want to add it to the equation 1, which is 2 moles of carbon dioxide, 2 moles of carbon dioxide, 2 forming 2 moles of carbon. So please always check if the equation is balanced when dealing with equilibrium constant, because the stoichiometry is needed to be used as the order of that reaction. So 2 moles of the carbon monoxide plus oxygen gas. So we are adding these 2. Okay. So this oxygen will cross this oxygen because one is at the reactant side, one is at the product side. So the overall reaction, what you are going to be having is that you're going to be having 2 moles of the carbon dioxide plus 2 moles of hydrogen gas, 2 moles of the hydrogen gas, 2 moles of the hydrogen gas, which moves to 2 moles of carbon monoxide, 2 moles of carbon monoxide, and then 2 moles of water. Is that clear?
Yes, Doc.
Okay, so 2 moles of water. Okay, so this, in balancing equation, they are all having coefficient of 2, 2, 2. So we reduce it to form to this particular form. Are we okay? How we got the overall reaction?
Hello, Doc.
Yes, sir.
Hello. Yeah, so does it mean to always get the overall reaction, you need to reverse the second equation?
No. It's just this particular one that we are dealing with, and we are just trying to prove, establish a relationship. It's not always that you reverse that. It's just about summing equation. By summing the equation, if you look at this overall equation that they said they have summed, basically what they did was that they reversed the one equation. Otherwise, if it is just summing the equation, you sum it up like we did here, we have done here.
Okay.
It's not like always you have to, you check the net equation and see whether one equation was reversed. Now, if it was reversed, then the new k here is going to be equal to 1 over the old k. So let me put this as new k 2 is going to be as the 1 over the old k2. You remember we established that relation. Once we reverse the equation, it's going to be a reverse of that. And then the old, this one, we didn't do anything. So it's still 1 K1 value.
K1. Okay.
Okay. So if we want the K3, which is the new K3, the new K, and we are going to say that it's going to have a relationship of, so K3 basically because we sum equations. Once we sum equations, we multiply the rates, the equilibrium constant. So it's going to give me the K1 times the K2 prime, the new K2 prime, or the K2, which, so the K2 prime. This relation that I want to just end up where, how did we get to have multiplying the K with that? And so we start with the K1. When you say K1, what is the equilibrium constant expression for K1? And what is the equilibrium constant for the K2? Or in other words, the new K2. So if you write it, K1 basically is just going to give you the concentration of the carbon, so the concentration of the carbon monoxide, raised to the power 2, which is all multiplied by the concentration of the oxygen, which is, multiplied by the concentration of the oxygen, divided by the concentration of the, divided by the concentration of the carbon dioxide, which is C2, and that concentration is also going to be raised to the power 2. Is that okay? So that's K1. Now plus we are summing it together. So how we ended up saying it should be multiplied, we are summing it together. And that is the K2 is also going to give me the concentration of water squared, water squared divided by the concentration of the hydrogen gas squared, also squared, multiplied by the concentration of the oxygen gas squared. Well, let's do the math here. So this is like fractions. We find the denominator, common denominator, which is this one multiplied by this one. You agree? So this multiplied by this one, and then that will be the denominator. Numerator will be this multiplied by this, and this multiplied by this. You agree?
You cross multiply.
Okay, so that will be the fraction. If you find that fraction, it should be equal to this K3. K3 is going to give you the concentration of the carbon monoxide squared, times the concentration of the hydrogen gas squared, hydrogen gas also squared. Okay, and that's divided by carbon dioxide squared. Sorry, this is water, not hydrogen gas. Water squared divided by carbon dioxide squared, and then the hydrogen gas also squared. So that's K3. So when we do the multiplication, we're going to end up getting this, which is in by effect trying to, I mean, if you look at how it is, it's just basically like saying multiply K1 by K2. So that relationship is what I'm trying to, I mean, this is messy. You can sit down and then try that and see. So this is the third thing that I'm trying to establish. So when we sum equations together, the new K becomes the multiply Ks of the individual equations that we have. So that's something which I want you to keep in mind. So you also keep this also. So when we sum equations together, the new K becomes the K of the individuals multiplied together. Okay, so three things before I move on. So a relationship, when I reverse an equation, it becomes one of the old equation which I reverse. When I multiply an equation by a factor, the new K becomes that old K raised the power, the factor which I multiply by that. When I sum equations together, the new K becomes the K's which I sum them together by it's just multiplying those new, I mean, the individual K's which I sum them together. So three relationships. You keep that also in mind as a point where we can just be having that. Okay. Well, I think I'm almost then I may want to, I just want to give you one or two examples and then maybe I'll stop it there and then I'll continue later by looking at the relationship between KC and then KP. Let me see if I can get you some samples to try. Okay. So let me bring my whiteboard. So can you try this if you, so what's in? So I'm putting some person on board. Then we'll try to see that. Okay. Okay, so can we try this? Then we can maybe take a break. I have to drink. So, can you see it?
No, dog. It's too. The font size is small.
It's too small. Let me see if I can increase that a little. Okay, so I'll bring this. So let's try this illustration. So the first, how about this? So I'm trying this illustration for me to see if you're following that. Can you see it?
Yes, dog.
No.
Okay, so it says that we should find a KC of this reaction following that the equilibrium constant follows this particular equation. What will be the KC?
I can't see. I don't know whether it's from my side.
You can see.
Yes, please.
So let's see if I can drag it. And then when I drag it, it spoils the font. How about this?
Please, it is better.
Okay. So what will be the KC without giving values? This is a complete question. I think let me put values there. Oh, I'm trying to find the complete question which has the values so that we deal with the entire values rules. Okay, so let's try this one then. I'm putting the values there so we look at it all together. Please write this in. I hope you can see it now. So we have to determine this with this data given us. So this reaction, we have half that reaction, and that is coming from this reaction of this and then this with this their K values respectively. So I've given you two equations, and I want to have the K value, the Kc value for this reaction. So what do we do? Please fast, tell me what will be the plan. How do we plan this question? So 2.6 times 10 to the power 30 is for the first equation, and then 1.2 is for this second equation, the K1, K2. So the K1 is 2.6 times 10 to the power 30. K2 is 1.2, which is for this equation. So how do I get the Kc for this reaction? What do I do? Oh, I thought we just finished this. So what do I do? So if you look at the overall reaction, you see that if I want to add this, where's my pointer? Okay, do you see something moving so that I'll use that to explain?
Yes, Doc.
Okay, so if you look at this overall reaction, it looks like this reaction has been reversed. Do you see it?
Yes, Doc.
So because the nitrogen here was at the product side, then here it is going to be at the reactant side. So it is being reversed. And this one is the same thing. We didn't do anything to that. Again, you see that this equation has been halved. So half of this equation. So it means that in equation one, we need to reverse it. We need to multiply it by half. So the derivation that we did, if I reverse an equation, the new K becomes 1 over the original K. You remember that. Now, if I multiply it by a factor, the new K becomes the new the K raised the power that factor which I multiply by that. So in this case, I'm going to reverse K1, which is going to be 1 over 2.6 times 10 to the power 30. Then I'm going to then multiply that K1 by half. I mean the new K, which I've gotten by now half. So it's going to be the 1 over 2.6 times 10 to the power 30, all raised to the power half, or in other words, square root of it. That will give me my K value now. Then the K2, which is still going to be that, because nothing happens in that. So if I reverse it, this nitrogen monoxide will cross this nitrogen monoxide because it's 1 mole, 1 mole. Now, this is going to go to the reactant side. So it's going to be 1 mole, 1 mole. So definitely the new Kc will now be the new K for K1 for this multiplied by the K2 for this. Is the explanation clear?
Doc, please, can you go over the last part?
Which part? So I'm just, I thought you would be doing that for me, or you want us to do it? So we are looking for this Kc, and that Kc gives us an overall reaction. Now, it's the overall reaction is derived from these two reactions. So we call this reaction 1, which will have its K1, which is this one. Then this second reaction will have its K, which is this one, K2. Is that okay?
Yes, no.
Okay. Now, what happens to the overall reaction which we are looking at? If I look at the two reactions, it means that the second reaction, I will not do anything to the second reaction. But then the first reaction, it looks like I've reversed the first reaction. Here, the reaction here says nitrogen and oxygen is at the product side. But if I look at the reaction which it says I should find, nitrogen and oxygen is at the reactant side. So it means that I need to reverse this reaction. By reversing this reaction means that the new K now becomes 1 over this K, original K. Clear? Is that
Yes,
clear?
sir.
Okay.
Yes, sir.
Now, it's not done. If I look at the overall reaction again, it looks like now the nitrogen has been halved. So I half the equation. So this one becomes 1 mole. This one becomes half mole, half mole. So that if it has been reversed, means that now the nitrogen now is at the product side, whilst the nitrogen monoxide is at the product side, whilst the nitrogen and oxygen is now at the reactant side. So if the nitrogen monoxide, which is 1 mole, is at the product, there's also 1 nitrogen monoxide there, so it will cross out. So now the overall reaction now becomes half of this bromine, which is plus half of this nitrogen, plus half of this oxygen, now moving to form the nitrogen monoxide bromide, this kind of bromate. So that is it. So if I should have it, means that the new K becomes the original, which is now 1 over 2 divided, raise the power, the factor, and the factor is half, which is like square root of it. Okay, that will now become the K1. So if I'm adding them, then the overall Kc here will become K1, the new K1, times the K2. Are we okay?
Hello, Doc.
Yes.
Their values, if we when we reverse the equation 1, it means that the
new K1
is going to be 1 over
2.6 times 10 to the power 30. Yes.
All halved.
All half.
Okay.
And then we multiply by 1.2. That will be the new Kc.
Okay.
Maybe I should, because I'm not writing, it's quite challenging for you. I'm putting this PDF there so that you can see that. Okay, so this is a question. Can you see my PDF?
Yes, Doc.
Okay, so this is a question. So from this overall reaction, this is what we are expected to have. So the KC, in fact, this is just trying to prove why we are saying that if you add two equations, the new KC becomes the multiplication of that. So it gives you the net KC for this equation. That's not our interest. But then if you consider equation 1, this was a KC value. And that in this overall reaction means that this new this K equation must be reversed. So when we reverse it, the new K becomes 1 over the 2.6 times 10 to the power 30. Then we half it again. So it becomes all raised to the power 2. So that's a value. And so if you want how the new K of this equation will be, it is going to be like this. I hope that enters well.
Yes, Doc.
Then we look at the second equation. Of course, the second equation, when we write the KC, is like this: the product minus O divided by the reactant, or is the power the orders, and then this is the value. So by adding them means that you are going to be multiplying the cases. So this a new KC1 multiplied by the new KC2. So we multiply this equation, we'll get to have the same as a net equation. That's why we are multiplying their K values. Does it make sense?
Yes, Doc.
Okay. So that is one example. I don't know if you are not tired, I can look for another example for you to try. Or I should just you have taken enough.
Yes, Doc. You are tired.
You have taken enough. Okay. So let me conclude that, and then we'll meet next week. So, well, next week I'll be looking at the relationship between KC and then KP. That is what you can read more on that. So, but as just a summary, we have just established that when we write the equilibrium, the first thing is to be able to know how to write the equilibrium constant expression. The equilibrium constant expression is when we are writing the concentrations in terms of concentration or in terms of pressure, the concentrations of the products, all of them raise the power their individual orders, and the orders is coming from the stoichiometric coefficient there because it's an elementary step reactions. Okay, and so we write that, and so the product divided by the reactant, that is the equilibrium constant expression. Then we also establish that whenever we have a reaction and then we reverse the equation, the new equilibrium constant expression is basically 1 over the original equation which we reverse, the equilibrium constant that we reverse. So 1 over K original. Now again, when we have an equation, we multiply by a factor. The new K becomes the old equilibrium constant raised to the power that factor that we multiply with. And then when we sum equations together, the new equilibrium becomes the multiplication of the individual equilibrium constant of this equation. So that is it. The next time we'll look at the relationship, and then we'll proceed to the factors that affect equilibrium reaction. Okay, see you. Or if you have any question, you can also ask.
Thank you, Doc.
Okay, so
Thank
then.
you, Doc. But please, Doc,
okay, so
I think we don't have this your slide.
I've given you the old slide. I'm now building this new slide.
Okay. Okay.
So I've given you what I used last year, but I'm
Yeah.
every year I try to add
Okay.
on
Update.
something. Okay. So I've given, for example, the analytical chemistry. I think I gave you some part, but then I saw somebody dropping last year's the whole file. So I'm updating that. I'll be dropping finally when I finish that. So there will be some few changes to that.
Okay,
so
sir.
that's what okay, see you then.
See you. Bye-bye.
Hello.
Yeah, hello.
Has the lecture ended? I went off a little.
Yes, ended.
Oh, okay. Thank you.